All right, let's continue our discussion of formal logic. This will be part two. We're going to focus on something called truth table. We're going to learn about a truth table test for deductive validity. Let's start with this argument. Suppose if it's Friday, my favorite TV show is on. Also, suppose further that my favorite show happens to be on. Can we conclude that it's Friday? This argument may seem valid, but if you think about it, it's not. Now, how do we know this? How could we prove or show this? Well, one way to do it is to talk through it or to think through it or to say something like, well, my favorite show is The Tonight Show, and maybe I'm watching it, maybe it's on, I'm watching it on a Thursday, but it's also true that if it's Friday, my favorite show is on. So I didn't say that my favorite show is only on Fridays, and then if it were on, it would be Friday. That would follow, but that's not what the first premise says. So that argument is invalid. So that's sort of an informal, talking through it sort of way to demonstrate the argument is invalid. But what logicians have done is come up with a formal way to determine validity. So they invented these truth tables. We can credit Ludwig Wittgenstein, an Austrian philosopher, with laying down the foundation for this method, this truth table validity test. And they can tell us whether or not these arguments are invalid. But to use them properly, we have to symbolize English into sentence logic, which we have done before. We also need to know the truth conditions for the kinds of sentences, the negations, conjunctions, disjunctions, so or statements, conditionals, the arrow or horseshoe statements, and the biconditionals. So let's start with negations. Negations have the opposite truth value of the statement they negate. So take a statement like Ryan lives in California. Let's say the symbolization is C. Then the statement Ryan doesn't live in California, the negation of that would be C with a negation in front. So the logic of that negation is captured with that tilde-looking symbol, that little squiggle in front of the atomic statement Ryan lives in California. So C, I live in California, and then not C, I don't live in California. And we can come up with a truth table for negation. So if you have some statement P and you have its negation not P, when P is true, then, drum roll, not P is going to be false. And if P is false, then the negation of it, not P, is going to be true. So it's just the opposite. So for any English statement that we symbolize, call it P. If P is true, then the negation of it, not P, is going to be false. And if P is false, then not P is going to be true. It's just the opposite, and that should be pretty straightforward and clear. So Ryan, let's say Ryan lives in California, is P, that's true. Then saying I don't live in California, that's false. That would be not P, and that would be false. But suppose that P is Ryan lives in Florida, that would be false. And saying that I don't live in Florida would be true. Conjunctions are and statements, and in order for them to be true, both parts, which we call conjuncts, must be true. So take this statement. If I promise to bring cake and ice cream to class, I need to bring both, otherwise I would be breaking my promise. So if P means I brought cake and Q means I brought ice cream, consider these four cases. Well, the first case is where I bring both and I tell the truth. But if I bring the cake, so P is true but false on Q, I didn't bring the ice cream, then I didn't come through on both, I'm a liar. Same thing if it's vice versa. If I bring the ice cream but not the cake, I said I bring both, so I lied. And certainly the case where I bring neither, then I'm a liar. In the first case, I bring both cake and ice cream, so P and Q is true, so this is a recap. In the other two cases, I failed to bring one or the other, so I lied. And that means that the statement P and Q would be false. So notice that it's very difficult for and statements to be true. It's only true in one of the four possibilities, when both cases are true. Now that's not the case for or statements or disjunctions. If I promise to bring cake or ice cream, then I really only need to come through with one of them for my statement to be true. As long as I bring one or other or both, I keep my promise. This is the way that a disjunction is true. The only way an or statement can be false is when both parts are false, are both disjunct. So we have conjuncts, the left and right conjunct for conjunctions, and we have the left and right disjunct for disjuncts. So here's the truth table, the characteristic truth table for disjunctions. So we have P and Q and its atomic components, P by itself, Q by itself. And if I bring both cake and ice cream, since I promise I bring at least one, we'll consider this inclusive or, that if I can bring both and that's fine, that would be true. If I bring just the cake and not the ice cream, then I still kept my promise because I said I'd bring or. I said bring at least one, maybe both. I kept my promise. If I bring the ice cream, not the cake, same thing. But if I show up empty-handed, it's false that I bring cake, it's false that I bring ice cream, then I lied. And so the statement, I brought cake or ice cream, is false, and that's the only time it can be false. Conditionals, these are more tricky. These are the if-then statements that we express either with the arrow or with the horseshoe. The only way a conditional, an arrow statement or horseshoe statement can be false is when the left side, which we call the antecedent, notice that prefix ante, meaning before, is true, and the right side, the consequent, like the consequences, what come after, is false. So if I made a deal and I said, if you get an A on the final, you get an A in the course, the only way I can break that promise is if you do your part, you do get an A in the final, and then I don't give you an A in the course. Here's the truth table for horseshoes. If both parts are true, the whole statement is true. This would be the scenario where you get an A in the final and I give you an A in the course. Yeah, I kept my promise. And then, of course, where I lied, if you get an A on the final and I don't give you an A in the course, where Q is false, then I lied. Notice this scenario is actually true, where you don't get an A on the final, but you still end up with an A in the course. The whole horseshoe or arrow statement is true, and that's because I didn't state that the only way to get an A in the course is to get an A in the final. I'm really saying here's a way. This is sufficient for getting an A in the course. It's not a requirement. So maybe you got an A on the midterm and you participated in quizzes and all those other things, and that's why you got the A, but not because you got an A on the final. And then, of course, if you don't get an A on the final and I don't give you an A in the course, that doesn't mean I broke my promise, so the arrow statement is still true. And so this just recaps all the things that I just said, so you can pause there and read through them if things are going a little fast for you. And then finally, we have the biconditional, the if and only if statement. So let's say the deal was changed. I said you'll get an A in the course if and only if you get an A in the final. So I'm not just saying it's a way. I'm not just saying it's sufficient. I'm also saying it's necessary. It's a way and it's the only way. So if you get an A on the course and Q is you get an A on the... if P is you get an A... yeah, sure. Okay, we'll keep it this way. P, you get an A in the course, and Q, you get an A in the final. My promise of you get an A in the course, if and only if you get an A in the final, can be symbolized as P tribar Q, or we can also use the double arrow. That also works. In our textbook, they use the double arrow, but in other books, other systems, they use the three lines, which are something's called the triple bar or the tribar. So here are the truth conditions for the what's called the equivalency or the biconditional, the tribar. Lots of ways to say it. When the truth conditions on both sides of the tribar are the same, that's when the statement as a whole will be the same. So if both parts are true, then the statement is true, like in row 1. But if one part is true and the other part is false, like in rows 2 or 3 here, the statement's false. If both parts are false, then the statement is true. So let's go through these with the you get an A in the course if and only if you get an A on the final case. So in row 1, you get an A in the course and you got an A in the final. And so my statement, if you get an A in the course if and only if you get an A in the final, holds to be true. And also, in the last case, if you don't get an A in the course and you didn't get an A in the final, then my statement was also true. But you can falsify is if you get an A in the course, but you didn't get an A in the final, that would serve to discredit what I said, and that's row 2. That would be an F. And in case 3, you don't get an A in the course, but you get an A in the final. That would make me a liar, so the overall statement is false. And we discussed row 4 there. We should also be really good at finding the main connective of our statements. So in our artificial language, remember we have these atomic sentences that we symbolize with these capital letters, A through Z. If we need more, we could use subscripts, but that's going beyond this class. And then we have our 5 connectives, or truth operators. We have the negation, the and, or the dot. You sometimes see it, the or statement, or the vel, the arrow or the horseshoe that represents the conditional, and the tribar for the if and only if. The main connective is the one that applies to the entire statement. So for instance, in this statement, not P and Q, the main connective is the negation. In P and not Q, the main connective is the and. It's the ampersand. It's the only thing that applies to the whole statement. It can't be the negation because that only applies to the Q. It can't be the P or the Q because those aren't connectives. In not P or not R, the main connective is the or, right? The first negation of that statement, it doesn't negate the whole statement. If we want to negate that whole statement, we would have to put parentheses around the P and to the right of the R, but it's only negating the scope, we say, of the negation just covers the atomic statement P. It's the or in the middle. That's the main connective. In the statement P, then R and not S, the main connective is the arrow. That's the only thing that applies to the whole statement. The P only is the P, R, and S are atomic sentences. They can't be connectives. Can't be the and. That only applies in the parentheses, and the negation only covers the S. In P, then Q, if and only if not R, it's the tribar. It's the main connective. The first arrow, the scope of that is only in the parentheses. The negation only negates the R. It's the tribar. In this statement, not P then Q if and only if not R, the main connective is the negation. That's negating the whole statement in the brackets. The main connective is not the tribar on that statement because the scope of it is only within the brackets and not the whole statement. So the first negation applies to the whole thing, but the tribar, it has no bearing on that left negation. We also need to be clear about the definition of validity. An argument is valid if and only if it's impossible for the premises to be true and the conclusion false. Here's the definition of invalidity. An argument is invalid if and only if it is possible for the premises to be true and the conclusion false. Here's a summary of the characteristic truth tables for all 5 of our connectives: negation, or, and, conditional, and biconditional. Notice that here we have the dot. The dot means and, just like the ampersand. And the horseshoe there, that kind of U turned to the rotated 90 degrees, that's the same as the arrow. So again, with the negation, it's just the opposite. With or, it's only row 4 where both parts are false. That's the only way to get a false or statement. Otherwise, it's true. For and, the only way to get a true statement is if both parts are true. Otherwise, you have a false statement. For the horseshoe, there's only one F there under that horseshoe or the arrow, we could have it, and that's when you have T arrow F. That's when you have the left side true and the right side false. Otherwise, it's true. So horseshoes and or statements are true 3 out of the 4 times. By conditional, you want to look at both sides. If they're the same, if they're both true, like in row 1, we get a T. If they're both false, like the last row, they're both false, then the statement is true. When you have the mismatch, that's when you get a false statement overall. All right, now we're ready to finally practice using the truth table test for validity. So let's say we have an argument. It's already symbolized here for us. A then B, A or B, thus A and B. So if we know that if A then B, and we know that at least one of these, A or B, maybe both, would it follow that we have A and B? It's not clear by just looking at it. So let's do a truth table test. So here's how you're going to do it. You are going to create a column for all the atomic sentences or statements that you see in the argument. I see A's and B's. So each one of those is going to get a column. So that's the left column. Columns go up and down, rows go left and right. So we have an A column and we have a B column. Then each premise is going to get a column. So we have a column for A, arrow B, and if A then B, and we have a column, that's column 4 from left to right for A or B, and then finally a column for the conclusion A and B. Now what about our rows? Well, we're going to have 4 rows for our truth values here, and that's because that's how many we need to capture all of the truth combinations. When we have A and B, and both of them can be either true or false, there's 4 possibilities. Either they're both true, they're both false, or one's true and one's false, and vice versa. That's the 4 combinations. To ensure we get all 4, it's standard to put TTFF under this left column. In this case, it's A. And in the second atomic sentence column, we put TFTF. So anytime that you have a truth table with 2 atomic sentences, you're going to have 4 rows beneath it, and the pattern TTFF for the leftmost, and for the right, for the left one. There's only 2 in this case, so we don't have to say leftmost, even though that follows. For the left column, TTFF, and for the right, TFTF, and that'll guarantee, 1, that we get all 4 of the combinations, and 2, that when you're doing your truth table, it's going to look like mine. So something extra that I do that isn't really covered in the book is I will make a landmine row at the bottom, and I will put a T underneath each premise column. So A arrow B is a premise column, A or B is a premise column, so that's going to put a T under that, and I'm going to put an F underneath the conclusion column. The conclusion follows the thus here. It's A and B, and at the bottom of that, I'll put an F. The reason for that is because this potential row represents a case in which both premises are true and the conclusion is false. And by definition, that's an invalid argument. If you go back and look at the definition of invalid, an argument is invalid if and only if it's possible to have true premises, and that's what this represents, and a false conclusion. So if we can show that that's possible out of these 4 possibilities, we know the argument is invalid, and that's exactly what happens. When we fill this truth table in, we're going to find a landmine. We're going to find a case in which the premises can be true and the conclusion false. So how do we fill in the rest of that table? Well, you have to look at the 2 atomic sentence truth values in those columns, and you have to fill in the rest of the boxes. So under A arrow B, we're going to fill in row 1 with a T, because that's the case in which both A and B are true. And you can almost hold or look at that set of rules, the set of basic truth tables for all of the connectives to help you fill this out. And if you look at it's a horseshoe one, but we know that's the same as the arrow. In that truth table, the only place where it's false is when the left side, in this case A, is true, and the right side, in this case B, is false. And that only happens in row 2 here. So it's row 2. I'm starting with row 1 with the truth column. So you could number those if you want to. So number 1 would be to the left of TT, which would be right under AB. And then row 2 would be TF, right under the column that starts with the column that has all the T's. Otherwise, the arrow statement is true. So we get T and then F, and then in the FT column, which I'll say is row 3, we have a case where the antecedent is false and the consequent is true. That's going to make the arrow statement true. And actually, an arrow statement, when both parts are false, believe it or not, the statement is false. Because remember the promise, if you get an A on the final, you get an A in the course. Well, if it's false that you get an A on the final, then I can consistently give you not an A. You can make it false that you get an A in the course. So I could still keep my promise in that case. Then we do the wedge statement. We do the or. Remember, the only way to make that false is when both parts are false. Where is A and B false? It's only in the FF row, row 4. Again, not counting the top row in this as a row. That's going to get an F there. And the rest are going to get T's. In the TT row, where A and B are both true, then the disjunction A or B will be true. Because if I say, is at least A or B true? Yeah, they're both true, so the statement's true. And in row 2 and 4, we also get T's, because in row 2, A is true and B is false. At least one of them is true, namely A. And in row 3, at least one of them is true, namely B. So we get a T there. Now what about the A and B column? Well, under that we put a T because that's the case where both A and B are true. So the whole statement's true. Under that we get an F. That's the case where B is false. And as long as one of the two is false, the whole thing's false. So if I promise cake and ice cream, this would be the scenario where I don't bring ice cream, so I lied. Under that, it's the scenario where I don't bring cake, so I lied. And under that, it's the worst scenario of all, the case where I bring neither cake nor ice cream. So my promise, I bring cake and ice cream, is false. So now we're going to walk through our truth table row by row, and we're going to treat it like a minefield, like we're in some battle, we're in some war, and we're trying to get across a minefield and survive. So in row 1, that's the row where A and B are both true, do we find the landmine, which is represented by, in this case, TTF, where the premises are true and the conclusion is false? We do not find that. We find TTT. So that row's safe. And then we take a step further into the minefield. This is row 2, the TF row. Do we find TTF? No, we find FTF. That row is safe. Then we take a third step into row 3. Row 3 is where A is false and B is true. Do we find the landmine, TTF? Yes, we do. That's a case where the premises are true and the conclusion is false. We hit the landmine. The argument explodes, which means it's invalid. That argument is not valid. That conclusion does not follow from the premises. Okay, let's go to an argument where there are 3 atomic sentences. We don't just have A, B, we have A, B, and C. And so for this, we need an 8-row truth table. And I'm just talking about the 8 combinations of T's and F's. So we could have a row where all 3, A, B, and C, are all true. We could have a row where A, B, and C are all false. That's row 8. We could have a row where A and B are true and C is false, or where A and C are true and B is false. And to make sure we get all those combinations, we'll have 8 rows, and under the leftmost, in this case it's A, it could be P or Q or Z, but in this case we have A, B, and C to keep it straightforward. Instead of T, T, F, F, we have 8 rows, and we will still do half T's, half F's. So we'll put T, 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 F, F, F. In the middle row, we'll have 2 T's, 2 F's, and then do it again. T, T, F, F, T, T, F, F. And in the rightmost row, outside rows, these are columns now. Columns go up and down. So the middle column is TTFF, TTFF. The right column with C, the third column, rightmost, is going to be rightmost for these atomic sentences, not the whole table. The C column, in this case, is going to be start with T and alternate. So TF, TF, and then do it again. TF, TF. And again, the reason we do that is twofold. Number 1, to make sure that we have all the truth combinations. We have 3 statements. They can each be true or false. It's going to give us 8 possibilities. And second reason, so that your table looks like mine. Now we need a column for each of the premises. We have 3 premises now. In the prior argument, we only had 2. So we have A or B, that's a premise, that gets a column. A, horseshoe or arrow, or then C, that gets a column. B, if and only if C, or B tribar C, or double arrow C, that's going to get a column. And the conclusion gets a column, C and A. And notice underneath those columns, we have 3 T's and an F. Before we had 2 T's and an F. Why do we have 3 T's and an F now? Well, because in the prior argument, we had 2 premises, so that's 2 T's. And we have 1 conclusion, that's 1 F, 2 T's and an F. But now we have 3 premises, so we'll get 3 T's and the F for the 1 conclusion. That's the landmine row. Okay, now we're going to fill this in using what we know about the basic truth conditions of our connectives. So start with A or B. We'll go down with that. Well, think about it. A or B. I'll bring cake or ice cream. The only way to make that a lie is if you bring neither. So look for the row where A and B are both false. And that's going to be in rows 7 or 8. Again, number them starting with the TTT row down to row 8, the FFF row. Row 7 and 8 are the 2 cases where A and B are both false. The rest of them are going to be T's. For the A, arrow, or horseshoe, or then C column, that is the if you get an A in the final, then you get an A in the course example. The only way to make a liar out of that promise is when you get an A in the final but not the class. So that's when A is true and C is false. Where does that happen? It happens in row 2 and it happens in row 4, and that's it. So we get TF, TF, and then a bunch of T's. All those t's are because F arrow T and F arrow F is going to make the statement true. That might sound like, how could two F's make a true? How is that possible? Well, if the statement is, for example, if you get an A on the final, you get an A in the course, and you don't get an A on the final, and you don't get an A in the course, does that make me a liar? No. So what I said is still consistent, still true. So that's why I get the true there. The if and only if statement, the B try bar C, you're going to look for sameness in truth value. So in row 1, B and C are both true. So we get a T in that place. In row 2, B is true and C is false. So we get an F in that case. In row 3, B is false and C is true. We get opposite. So again, we get an F. In row 4, they're both false. They're the same. So the B try bar C is true there. And then notice we have a repeat of that. So we'll have T, F, F, T again. And then finally, the AND statement. AND statements, it's hard to make them true. If I promise cake and ice cream, I got to bring both for it to be true. And that only happens, so we're looking at C and A. C and A are true only in row 1 and in row 3. That's where C and A are true. Otherwise, you have at least one F there. In row 2, C is false. In row 4, A is false. And A is false all the way down from, A is false in row 5 through 8. And C is false in row 4. But as long as one of them's false, the whole thing's false. So it's F, F, F all the way down to row 8 in the C and A. So now we start to walk across our landmine. So starting with row 1, we see T, 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 4 T's. And that row's safe. No landmine there. We're looking for T, 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 F. Is row 2 safe? It is. It's T, F, F, F. That's not T, 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 F. Is row 3 safe? T, T, but we get an F. But that's okay because we went triple TF. Row 4, is that safe? T, F, T. We already know that it's safe. But row 5, we're trying to cross the minefield. We're at row 5, where A is false, B is true, and C is true. Premise 1 is true. Premise 2 is true. Premise 3, true. Triple T, and then the conclusion is false. Oh my God, it matches up. And we hit the landmine. The argument blows up. It is invalid. So if you know that at least A or B is true, and you know that if A, then C, and you know B, if and only if C, then C and A do not follow. It is possible to have true premises and a false conclusion. This argument is invalid. Now, some of these truth tables can become very cumbersome because they have so many rows. So when you have 3 atomic sentences, then your truth table is going to be 8 rows. And it's going to double with every atomic sentence that you add. If you had a 4 atomic statement argument, then you would have 16 rows. If you had a 5 atomic statement argument, you'd have 32 rows. So sometimes there's a shorter way to do this truth table. It's the short truth table. So let's practice with a really short argument, and then we'll look at a harder one. Let's say we take this argument. If it's Monday, my favorite TV show is on. It is on. It's Monday. We looked at an argument like this. We would symbolize it like this. If M, then S. If it's Monday, my favorite show is on. My favorite show is on, so then it's Monday. Now, if we write the argument out left to right, so premise 1, M horseshoe or M arrow S, premise 2, S, and M, let's just assume that we'll hit a landmine. Let's assume there's a landmine row. And the landmine row is where we have a T underneath each premise, right, under the arrow or the horseshoe, and underneath premise 2, which is S, and we will have an F underneath the conclusion. So if we can make this work, then we know the argument is invalid. Let's see if we can do that. Well, we need to be consistent with our letters, and we need to make sure that the logic of the connectives or the operators works. Well, since S is true in the second premise, it's got to be true in the first premise. So that T should be a little bit more directly under the S. I apologize there. And since the M in the conclusion is false, it should be false in the antecedent of the premise. Now let's check to see that the logic works. Are arrow statements true when the left side is true and the right side is false? They are. only way arrow statements are false is when the left side's true and the right side's false. So we're done. We've shown that this argument is invalid because we've shown it's possible to have true premises and a false conclusion. So again, so this is recap. We have to check two things. One, make sure we're consistent with the truth values underneath the sentence letters. So all the S's are true, all the M's are false. And two, we need to make sure the values under the connectives are consistent with what we know about the truth conditions. So there's only one connective, the arrow, and that is okay to say that it's true, and that's because an arrow would be true if the left side's false and the right side's true. We've literally shown that it's possible for the premises to be true while the conclusion is false, so by definition, the argument is invalid. Let's look at a more complicated argument. So this has P, Q, R, and S. This has 4 atomic sentences, so this would be a 16-row truth table if we did a long truth table. So we're going to find the main connective of each premise. So that's the negation of premise 1, not P and Q. It's the arrow of premise 2. Premise 2 is P and R, horseshoe or arrow S. And that S maybe should be a little bit closer to that arrow, but so be it. And the third premise is just S. And so I apologize. That F should actually, where should it be? You could pause and figure it out. That F should be under the wedge, underneath the little vel, not under the P there. So just with the way that the PowerPoint laid it out, it's shifted a little bit off. So I apologize for that. So let's be consistent with our letters. We know that S is gotta be true in the second premise because it's true in the third premise. We know that since the or statement is false, we know that both parts of the or statement and the conclusion are false. So that F should be directly underneath the P. There should be an F underneath the wedge, and that negation before the R is false. And right, because we're assuming the conclusion is false, that's the or. So we have a false or statement. The only way an or statement can be false is when both parts are false. Well, the left part is P, so we know P is false. And the right part is not R, so we know that the not part of the R is false. So that means that the R has got to be true to make not R false. And we also know that the P in the first premise has to be false because in the conclusion it's false. We got to be consistent. And we also know that the P in the second premise is false to be consistent. We know that the R has got to be true because not R is false, and the negation just flips that. So the R in premise 2 has to be true. What else do we know? Well, we know that the and in the first premise has to be false. Why? Well, because the first premise we're assuming is true, and since the first premise is the negation of an and statement, if the negation is true, then the and statement has to be false. And with Q, it doesn't really matter what we make Q, and that's because either way, it's going to lead us to a false conjunction. If we made Q false, it would have a false conjunction, and even if it's true. So now we have to check it. Are all the letters the same? Well, all the P's are false. In premise 1, false. In premise 2, false. And in the conclusion, false. Yes. Are all the Q's true? There's only one. Got it. Are all the R's true? Yeah, it's true. And then that R, the R in the second premise is true. And in the conclusion, that should be nudged over a little bit more. It's true. Are all the S's true? Yeah, both of them are true. Now we have to do the connectives. Well, the left negation in the premise is true because it's negating a false and that and is false because at least one part is false. The and in premise 2 is false because at least one part is false, the left part. The arrow in the second premise is true because we don't have T arrow F because the antecedent's false and the consequence true. That'll make that true. And then the not R is the flip of the value, so that works. And then the or in the conclusion is false because both parts are false. So we've shown that that argument is invalid because it's possible to have true premises and a false conclusion. So if you want to practice on your own, here are some arguments that you can do with short or long truth tables. And I think there's more practice on our website. So thank you for listening. If I went fast at any point, remember you can always pause. You can also always listen to something over again. All right, see you next time.